Project Bearkite was an attempt to familiarize ourselves with the system engineering principles in an attempt to accomplish a specified goal. It combined a structured approach in designing a kite with the fun of getting a chance to test our design with flight tests. The first step in this process is to state the system requirements. We needed to design a kite using a system engineering approach, make sure the kite flies, come up with 3 unique tail designs, and validate the performance with flight tests. The project also needed to cost no more than about $15. In order to get an idea of where to start with our design, we used NASA's Interactive Kite Modeler version 1.5a. This program allows you to choose a basic kite design and change the size and the materials used. Based on the unique user input design, this program can give theoretical values of lift and drag. Based on the data we received from this program, we decided for the design to be a sled kite.
The pattern is cut from ripstop nylon, which is very durable. Wooden dowels act as longerons, which are sewn and glued to the fabric. A bridle line is sewn to each wingtip and then sewn together at the control line. All lines are made of inexpensive cotton string that is wound up on an inexpensive plastic controller.
Yep.
Drogues act on the principle of drag. The greater the wind, the greater the resistance, and therefore it stabilizes the kite. For our application, the wind speeds were not very high, and the drogue didn't make much of a difference. It only added weight and ended up only decreasing the lift. The vertical stabilizer was a complete failure. It fell off immediately as the kite took flight. The idea was to reduce the effectiveness of the crosswinds, which would typically put the kite on the ground, much like a fin stabilizes a plane and reduces side slip angles. Again, it never did pan out. The streamers were the most successful tail design that we came up with. It added a lot of stability to the kite, as you can see in the video. It never did quite reach the same lift as the kite without a tail, but it was definitely the most successful of all of the other tails.
Call it. Yeah, I think 70. It says 110.
The wind speed is the biggest contributor to the lift to drag ratio. As you can see, as the wind speed increases, with Kevin running to increase it, the lift increases. Once the angle can be approximated, the following calculations are made. The percent error is acceptable given the inconsistency of the wind speed and the way in which the angle with the horizontal is measured. It could have been a lot worse, and in some cases it was a lot worse.
All mixed up, you don't know what to do. Next thing you turn around and find a person is you.
The mission was an overall success. Not only were we under budget, but we adhered to all of the system engineering requirements. Our flight predictions were within an acceptable degree of error given the unpredictable winds. But most importantly, we had fun. And let go of regret.